So, good morning to everyone. Can somebody tell me, please, am I audible to you?
Yes, sir, you are audible.
Okay. Thank you so much.
Sir, your voice is not coming.
Hello, am I audible now?
Yes, sir.
I don't know what is it. Okay, that's fine. So, did I explain this slide to you already? Did you hear me that time?
No, sir. No, sir.
So what I was telling that the receiver function is a very popular and a new technique, and it has been going on since from the last 35 or 40 years. And if you compare it with the techniques that are used to find out the structure of the Earth, imaging techniques, then it is relatively new, and it is basically used to image the abrupt changes in the discontinuities or the jump in the p and s wave velocities. And if after you locate those discontinuities, the changes in p and s wave velocities, it is very important to investigate the tectonic evolution uh, of the lithosphere. And this technique is basically used to image the crystal structure if you are considering a radial receiver function, but it is also equally be applicable for finding out the upper mental structure if you are using the S-wave receiver function. So the waveforms in the receiver functions contain the information related to the source time function, propagation effect, also the propagation effect of the mental and local structure underneath the recording site. So the basic concept is that when so this is basically if you compare the receiver function technique with the other technique, so there are some pros and cons also, like disadvantage and the advantage if you compare it. So like there are three popular techniques that can be talked about, like inversion of travel time curves, wide angle observations. Yeah. So wide angle observations and also the body and surface tomography. So the inversion of travel time curves, the travel time curves you have already seen in the previous classes. So the if you are inverting the travel time curves, so like in 1914, Gutenberg did that, and he could find out the existence of the liquid outer core using the inversion of travel time curves. Like if you will talk about wide angle observations, then it is considered to be effective to explore the crystal structure, but it has some difficulty in identifying the low velocity curves. Likewise, if you will talk about body and surface wave tomography, then it is important to study the upper mental, and it is sensitive to the gradual variations uh, in velocities, but it is not quite effective for exploring the sharp discontinuity. So this is the place where yes, am I audible?
Sir, we lost you in between.
How about now?
Yes, sir.
Should I explain the slides again? This one?
Just the last point that you explained from there.
Okay. So basically, this slide was prepared to show you the brief comparison between the.
Sir, the slide is not visible.
Okay. I think I should. Okay, and my video is already off. Okay. So it's visible now.
Yes, sir.
Okay. So in this particular slide, I actually put a brief comparison between the previously employed techniques and the receiver function techniques. So so there are three important techniques which are employed in the field of seismology to image the deep earth structure. One is the inversion of travel time curves, another is the wide angle observations, and the last one is the body and surface photograph. Although there are many other techniques, but these are the most important ones. So using the inversion of travel time curve, uh, the existence of liquid outer core was identified by Gutenberg in 1914. And if you will talk about by wide angle observations, it is actually effective to explore the crustal structure, but it has some difficulty in identifying a lower velocity load. And if you talk about body and surface wave tomography, it is actually important to study the upper mantle, and it is sensitive to the gradual variations in the velocity, but it is not considered to be quite effective for exploring the sharp distances. So in this particular case, when the surface wave tomography fails to explore the sharp discontinuity, receiver function plays its important role quite efficiently. So if we talk about receiver functions development, the original concept of receiver function methodology was developed by Finney in 1964, model the spectral amplitude ratios of teleseismic P waves by finding the ratio of the Fourier spectral amplitude of the vertical displacement to that of the radial displacement of the incoming P waves. So if you so Finney, what he did, the advantage of that was that you don't have to know the incident P waveform. The knowledge of the incident P waveform was not required. So it was a very important, and I would say uh, it was an innovation that actually brings a lot of things into the seismology. So, but the drawback with the technique the Finney developed was that it did not step further to transform this result from frequency domain to time domain, uh, such that the timing and the amplitude of the individual phases with the spectral ratios method remained unknown. And then this breakthrough was achieved by and we could model the observations directly into the time domain. And also he estimated the source time function and uh, and was able to compare the synthetic seismograms in time domain directly to the data. And he also developed a deconvolution technique to equalize the effective source time functions and to remove the instrument response. And after that, Owens in 1984 applied the technique to broadband waveform data and extracted the receiver function. And then in the last 30 years, several things have happened in the field of receiver functions for the separation of S and P wave. Like quite well-known figures are Langston, Owens, Ammon, Ligoria, and Ammon, who developed the iterative time domain deconvolution technique, and then waveform fitting, time depth transform, and the stacking and migration techniques were developed by Yuan in 1997, so that lateral variations of the discontinuities in the crust error fundamental can be investigated. So the question comes, what is a receiver function? Yes. So here you are seeing this is a incident plane P wave, which is actually traveling from a teleseismic distance and impinging upon this high velocity contrast, or you may say discontinuity. So after it impinges upon this discontinuity contrast, it gets converted into S wave and also generates the P wave coda into this structure of the Earth. The dead dashed lines are representing the S wave and the solid black line is representing the P wave. So you can see this is the P2S converted phase and this is the direct P phase and these are associated reverberations. And these reverberations and the P2S converted phases along with the direct phase, you can see into this receiver function. So this is the direct phase, PP phase, and this one, the green one is the P2S converted phase, and PPPS is the multiple, and another reverberation is the PPSS plus PSPS phases. So if you have the knowledge of the background velocity model, then you can model the amplitudes of these converted phases and the timing of these converted phases so that you can supply valuable constraints on the underlying geology. Basically, you can find out the depth to this discontinuity if you can model these reverberated phases and the converted PS phase using the background velocity model. And so if we talk about types of receiver functions, there are majorly two types of receiver functions, P receiver function and the S receiver function, which are also sometimes called as PS receiver functions or P2S receiver functions and also known as the radial receiver function. And there is another type that is S receiver function, which is also known as, in some literature, you will find it to be called as SE receiver function and or S2P receiver function, and also known as vertical receiver function. There is another type of receiver function as well, which is known as transverse receiver function. So these are the typical diagrams of the receiver function. So this one that you are seeing, it is the P wave receiver function, and this is the S wave receiver function. And in the P wave receiver functions, the converted phases and the multiples comes after the direct phase, because if you look at the S wave velocity, which is slower than the direct P wave velocity, so the converted phases will come after the direct P wave receiver function, P wave, and then in S wave receiver functions, the S2P converted phases, because P phases are faster than the shear wave velocity, then it will come earlier than the direct S phase, and the SP phase will come earlier than the direct S phase. So there is one advantage for the S wave receiver function is that the S wave receiver functions are considered to be free from the multiples, and it can also be used to image the upper mantle structure because it has higher wavelength if you will compare it with the P wave receiver function. So these receiver functions are the synthetic receiver functions, and these synthetic receiver functions are actually constructed for this velocity structure. You can see on the y-axis there is depth given in kilometers, and on the x-axis the shear wave velocity in kilometers per second are provided. So you can see there are two jump in the velocities. At MOHO, the velocity is increasing pretty sharply, and at LAB, the velocity is decreasing sharply. So these discontinuities can be imaged by these receiver functions. So if I would say that P wave receiver function is most suitable to identify this MOHO velocity contrast, and S wave receiver function is suitable to identify LAB contrast, although P wave receiver function can also identify this LAB, but not as good as in the case of, if you compare it with the case of S-wave receiver function. So, what is the mathematical approach to compute receiver function? So, when any earthquake happens, basically the earthquake source released a source pulse, which is actually shown by this source time function st, and when it gets convolved with the impulse response of the earth structure and also to the instrument response of the receiver, then what you see as a record on the receiver is known as seismogram. And this seismogram is also known as seismic waveform recording, which is basically denoted by T. And our main goal is to find out this E, because you want to find out the impulse response of the local earth structure. So, in order to do so, what you would like to do from the seismic waveform recording, you would like to remove the instrument response and also would like to remove the effect of the source time function or the seismic source function in order to get the value of E. So this is the receiver function is all about to find out this E value, the impulse response of the local earth structure, or in sometimes it is also called as the reflectivity series of the earth. So there are some fundamental assumptions before we proceed upon to compute the receiver function. The fundamental assumptions are the P wave that is impinging upon the discontinuity of high impedance contrast should be a plane wave. That means by this means the P wave should be arriving around more than 30-degree epicenter distance. So when any source energy coming from a larger distance, the wave front associated with it will be looking like as a plane wave front. So this plane wave approximation is very much needed, because there is another reason also. If a wave is coming from a larger distance, then it can sample the lower mantle and upper mantle as well, because it will, as you know, like if the tip of angle is smaller, then it can dive deeper into the earth structure and can sample the deeper structure. And the PS is the second assumption is the PS converted phase, that is the phase which is primarily recorded on the radial component.
Sorry, your voice is broken.
Okay. Am I audible now?
Yes, it is better.
Hello.
Yes, sir, it is better now.
I'm sorry. I think there is some network issue over to my end. I don't know why is that happening. Okay, no problem. So, should I explain this slide again?
Yes, sir.
Okay. So, when you compute receiver functions, there are some fundamental assumptions associated with it. So, first assumption is that the incident P wave energy should be of plane wave nature, which means that the energy should be coming from a very large distance. So, in seismology, before we compute receiver functions, we try to scrutinize all the seismic waveforms which are coming from more than 30-degree distance if you are computing the P wave receiver functions. So, main reason for doing is that the energy which is coming from a larger distance will be having a smaller takeoff angle, can also sample the features that are available in the upper mantle and also the lower mantle. And another assumption is that the PS should primarily be recorded on the radial component. That is the assumption that the P2S converted phases will be only available on the radial component, and the almost negligible energy will be available on the vertical component associated with the P2S converted phases. And so after you consider both of these assumptions, it will lead to the result that the receiver function only includes the P2S converted energy. If you are talking about the S-wave receiver function, then it will only consider the S2P converted energy. So if we talk about receiver functions definition, so the receiver functions basically considered as the time series computed from a three-component seismogram, and it actually used to show the relative response of the Earth structure near the receiver. So this is the same diagram which I am showing over here, and which is where you have the incident P-wave energy coming from a teleseismic distance, because we are considering the plane wave approximation. And when it impinges upon this discontinuity of high impedance contrast, then it gets converted into the S wave along with its several other reverberations. And if you know the amplitude and the timing of these converted phases with respect to the direct P wave, then you can model those amplitude and the timing to actually find out the constraints on the underlying geology. So there are basically two main steps for the computation of the receiver function. One is the rotation, and another one is the deconvolution. And before you even perform both of these steps, there is another pre-processing step where you would like to remove the instrument response from the seismic waveforms in order to compute the receiver functions. So basically, what you so for the removal of the instrument response, there are several utilities available. Like in fact, you can use transfer function. There is a command transfer that can be used to remove the instrument response using the pole and zeros file and the response files, that are the files which actually contains the information about the instrument. And then you would like to perform the rotation so that you can concentrate the energy of P wave on the mostly on the vertical component, SV wave on the radial component, and the transverse component will contain the energy related to the SH wave. So there are basically two important rotations. Sometimes like people do rotate the vertical north-south and east-west component to ZRT component. That means vertical, radial, and the transverse component. And sometimes people also do further rotation in order to have a more focused energy of P wave on the L component and SV wave on the Q component and the SH wave on the T component. So as it has been told earlier, radial component means the direction that is joining the source to the receiver, and T is the direction in the along the SH wave energy, and L is the component which basically contains the direction of P wave energy, and Q is the SV wave and T is the SH wave energy. Likewise, deconvolution. So this is the Earth impulse response, which is represented by H here, H in frequency domain, omega. And here you are deconvolving the radial, Q component, deconvolving the L component from the Q component. And for computation of the SP receiver function, you are deconvolving the Q component from the L component. So, if in order to do the rotation, as I told you earlier, So if you are going to do E, Z and E, that can be vertical, north, south, and the east-west component are two vertical, radial, and the transverse component, then you will have to rotate it using the value of the back azimuth of the event that you are having in your seismogram. So this is the rotation matrix or transform matrix you can say, and which is used to actually compute the radial and the transverse component for the rotation. And if you would like to do the further, if you would like to do the further rotation into LQT component, then this is the transfer matrix you would like to use, where you have A as the BA as the back azimuth, and I is the incident angle. So this incident back azimuth is almost always applied with the data, but this incident angle you will have to find out by some means. There are methods to compute the incident angle. So the most so one of the most prominent method is the minimization of the P wave energy onto the receiver function. So in that method, like yes. So basically, so my screen is visible.
Yes, sir.
So now I have changed to OneNote. Is it visible? My OneNote is visible to you?
No, sir. Slides only visible.
Okay, that yes. Okay. Now it should be visible to you. Is it?
That's the same slide is visible, sir. Same slide.
Okay.
Rotation one.
Right. So now it should be visible by OneNote. Okay,
Yes.
so yes, so this is what this I is the incident angle, and it is important to find the value of this incident angle by some means. So basically, what it is done, uh, so what it is done, we actually vary this value of phi. Maybe let's suppose you are varying this value of phi from let's suppose minus 40 degree uh, with a step of 1 degree to let's say around 60 degrees. And for each step, you will rotate your seismograms. Okay, so let's suppose you have vertical component, radial component, or maybe sorry, north-south component, sorry, vertical component, north-south component, and the east-west component. And using the first value of phi, let's suppose that is minus 40 degree, you have rotated your component to L, U, and T, and then using these, you have computed P receiver functions. Okay, that how would you do that? Just do the deconvolution of deconvolution of the vertical component from the radial component to get the value of to get the receiver function, P wave receiver function. So let's suppose your receiver function may look something like this. Okay, so this is your direct P phase, and this is your PS phase. This is your PS phase, and here you have the other reverberations like PS plus PP SS phase. Okay, so don't be confused with this capital and the small letters, because if you look at my previous slides, I think I should have told you about that. Yeah. So if you look at this slide, there are some letters with a small in a small and some are in capital. So like for the incident energy, the letter will always be capital. Okay, that is capital P. And when the wave is upgoing in the layer, then it will be always a small letter. So in this case, if you are talking about P to S converted as wave energy, then it is P and small s. And likewise, if you talk about this PP PS phase, then the incident energy will always be capital P, and then this is the upgoing wave, so it will be small p, and then it is getting reflected back from the surface downward, so it will be capital P, and then it has converted to S wave that is upgoing, so it is small s. So for in the layer for upgoing, you will have a small letter. Within the layer for downgoing wave, you will be having the capital letter. And incident energy will always be capital. So here, you can, so these are the, so this is the direct phase, this is the converted phase, this is the multiple, and these are other multiples. This basically mixed with two kind of multiple, PSPS and PPSS, because, and these comes almost around the same time. So that is why it is written PSPS plus PPSS phase. So after you compute the receiver function by using this 40-degree value, minus 40-degree incident value, then you will again compute another receiver function by using the same deconvolution methodology at around minus 39 degree. Likewise, so let's suppose this is minus 39. This is another receiver function. Likewise, at 38 degree, you will compute another receiver function. Okay, so you will keep on checking, keep your eye on the amplitude of this direct P wave energy. Whenever at whatever incident angle between minus 40 to 60 degree, this energy of the direct P phase will become minimum or almost zero. That value associated with the incident angle will be the real value that you would like to incorporate into this 3D rotation matrix. Okay, into this matrix, so that you can get the actual value of the LQG component for using that incident angle. So now that you have performed the rotation, the next step is the deconvolution. Okay, so deconvolution basically can be done in frequency domain and also in the time domain. So the ideal case is that, so in order to find out the impulse response of the earth structure, you will have to deconvolve the radial component in frequency domain from deconvolve the vertical component from the radial component. Okay, so in deconvolution, you will have to multiply both the numerator and the denominator by its conjugate. So this is the ideal case that you will have to follow in order to deconvolve the vertical component from the radial component. So sometimes you may think like, why we are deconvolving the vertical component from the radial component. So the assumption is like that in the case of PS receiver functions, what we consider the vertical component, that is the red. The vertical component contains the information about the source, and the radial component contains the information about the source plus reflectivity series or the impulse response of the earth structure. Okay, of earth structure. So by deconvolution, you would like to remove the effect of the source pulse from your radial component. So for that purpose, to compute the earth response, what you will do, you will deconvolve the vertical component from the radial component so that the impulse response of the earth structure, the only thing that will remain into your receiver function. So that is why we are deconvolving the vertical component from the radial component. And also Langston actually devised this technique in 1979, and what he did, he simplified his results by incorporating a Gaussian filter, low pass Gaussian filter into the deconvolution technique. So what he did, he actually multiplied the denominator by the Gaussian Wilks parameter. So multiplied it with the Gaussian filter. So the Gaussian filter is a low pass filter which is basically having a simple phase shape and the zero phase distortion, and also it has the lack of side lobes. So don't have to worry about that. Okay, so this is the ideal case. So in ideal case, if you will just do that, then your receiver function should be computed. But this is not always true, because in the denominator there are some frequencies which has very small amplitude or almost zero amplitude. If those amplitude, those small or zero amplitude will be in the denominator, then the stability of the deconvolution will not remain intact. You will have your stable deconvolution will be compromised. So what you would like to do in the not ideal case, you would like to attenuate those frequencies which have a smaller amplitude or almost zero amplitude. So for that purpose, there was a technique that was proposed, which is known as water level deconvolution technique. In water level deconvolution, uh, uh, the way we avoid division by a small number is to replace the small values in the denominator with a fraction of the maximum value. And that fraction is basically known as the water level parameter. So you can see it is so this water level, so that fraction you will have to multiply. So what was our ratio function? R omega by G omega multiplied by its conjugate, and also with Gaussian filter, and then you will have to multiply this denominator by the fraction of the maximum value, so that you can replace the frequencies that are having a smaller amplitude or the zero amplitude by some number, by some bigger number, so that, or you may replace those, you may actually remove those frequencies completely, and that particular fraction is basically chosen by trial and error method. So the consequence of replacing small values with larger values in denominator is an attenuation of the frequencies for which the vertical component has a small amplitude. And if you will talk about that fraction or water, so that fraction, which is also known as the water level parameter, at times the water level can act high pass filter, low pass filter, and the notch filter, or you may say the filter which can actually let some frequencies to pass through. So that is known as notch filter. And then, so this is the diagram which can actually, so this is the diagram which can actually explain this phenomena. So basically, what you are doing in here is that, so in the denominator you have vertical component. So this vertical component, after you do the fast Fourier transform, then you, let's suppose you have, uh, so basically after you do the fast Fourier transform, then you can see all the frequencies and associated amplitude within this spectral seismogram. So here you have frequencies, here you have amplitude. So by doing so, by doing the FFT, you can get to know which frequencies are having the smaller amplitude or more zero amplitude. So these frequencies here you can see are having the smaller amplitude, and we need to attenuate these frequencies. So for that purpose, you will apply a water level to it. The water level means you will just do the water level. That means you are removing the low frequencies, so sorry, low amplitude frequencies, and will only be remains with the frequencies that are higher to that water level. So that is what it is happening here in this particular figure. So amplitude spectrum with water level highlighted. So this is this blue thing that you are seeing. This is the water level, and when it is applied, then only the amplitude which are above this water level will remain to be incorporated in the deconvolution. Likewise, so we have talked about frequency domain deconvolution. Likewise, there is another deconvolution technique that is known as iterative time domain deconvolution technique, and it was basically developed by Liguria and Ramon in 1999. So this technique is basically based upon least square minimization. Okay, so in this, as I told you, the basic assumption was that the vertical component contains the information about the source, but radial component contains the information about source, and also it contains the Earth impulse response. Okay, and it contains the information about the source. So, so, so what they are doing, first they are trying to cross correlate the vertical component with the radial component to basically estimate the length of the first and the largest spike in the receiver function. So it is a iterative approach. So first they will try to find out the Earth impulse response by just cross correlating the vertical component with the radial component, so that they can find out the lag of the first and the largest spike. And then after they get this spike, they would like to convolve it with the vertical component, so that if this is the true Earth response, true Earth's impulse response, when you will convolve it with the vertical component, it should essentially give the radial component, right? So likewise, in the second iteration, they will improve the spike or add more spikes to it, to the Earth impulse response, and then again convolve it with the vertical component to get the another radial seismogram. And then at each of the steps, they will compare this radial, the synthetic radial seismogram with the observed radial seismogram, and try to find out the misfit. Okay, in the least square sense. So they try to find out the misfit, and then at each iteration, by either improving the spike or removing the spike or adding more spikes to it, they will try to actually compute more and more radial seismogram, and then calculate the misfit with the observed radial component, so that after certain number of iterations, the misfit should be minimized. Whenever the minimized value of the misfit you will receive, the associated Earth impulse response like this will be considered as the true value of the receiver function. So this is the iterative tide-water deconvolution. So in receiver function estimation, the foundation of the iterative deconvolution approach is the least squares minimization of the difference between the observed horizontal seismogram, horizontal means radial component, and a predicted signal generated by the convolution of an iteratively updated spike train with the vertical component seismogram. So for this discussion, they have assumed that we are estimating the radial receiver function. So the approach that I just explained to you, it is applicable to radial receiver function, but the approach is equally applicable to the transverse motion as well, and can be easily generalized to accommodate simultaneous deconvolution of any number of signals. So in this process, first the vertical component is cross-correlated with the radial component to estimate the leg of the first and the largest spike in the receiver function. The spike amplitude is estimated by solving a simple equation listed in Kikuchi and Kanamori 1982. Then the convolution of the current estimate of the receiver function with the vertical component seismogram is subtracted from the radial component seismogram, and the procedure is repeated to estimate other spike legs and amplitude. With each additional spike in receiver function, the misfit between the vertical and the receiver function convolution and the radial component seismogram is reduced, and the iteration halts when the reduction in misfit with the additional spikes becomes insignificant. So is there any question from anyone so far?
Sir, I have a question from rotation.
Yes.
Is it same applicable to S receiver function also, rotation part?
Yes.
Like type of rotation we can do for S receiver function also, right?
Yes.
Okay. So there we have.
It's a simple code that you can write by your own also. But you are just minimizing the amplitude of the direct phase. If you are doing it for the S wave receiver function, then the direct S phase at whatever incident angle value will be minimized. That incident angle value will be the true value of the incident angle.
So direct S wave energy has to reduce on radial component then. In S receiver function, which component we have to check?
So in S receiver function, you are basically deconvolving the radial component from the vertical component, because you are basically looking for the converted S to P energy. Okay. So our assumption, as I told you in the beginning, is that the P wave energy is mostly concentrated on the vertical component, S wave energy on the radial component. So if you would like to have the knowledge of the P to S to P converted phases, then you will have to deconvolve the radial component from the vertical component.
Okay. Thank you.
Any other question? So, okay, I am taking a 5 minutes break. We will meet after 5 minutes.
Sir, you are not audible, sir.
It's a 5 minutes break.
Am I audible?
Yes, sir.
Yes, sir.
Okay, let's move forward. So the diagram that you are seeing in front of you, it is basically a cartoonistic diagram of the behavior of the receiver function in the case of different kind of discontinuity structure. So how the receiver functions are sensitive to discontinuity structure are explained briefly by this figure. So in this particular figure, that you see that here is the depth, and on the x-axis you have either VP or VS. So if you consider VS, then you can see the velocity is pretty much constant up to this particular depth, and then it is sharply increasing, and then again it is becoming constant after that particular discontinuity. So here the sharp increase in the velocity is happening, the depth at which this is actually a discontinuity here because it is having a sharp change in the velocity. uh, so this is the discontinuity. So the response of the receiver functions for this particular structure will be maybe something like this. So this here, you can see this is the direct P phase, and here is the converted PS phase. So if you look at this kind of velocity structure, this one, here you will see the velocity is pretty much constant up to this step, and then it is gradually increasing and becoming constant. And the response of the receiver function will be like this. And here you are seeing the velocity is constant up to this step, and then there is a high velocity zone. That means the velocities are anomalously high, and then again it decreases, and then it becomes constant in this part, and then it again increases pretty sharply. For example, at Moho or 410 kilometer discontinuity or maybe 660 kilometer discontinuity, and then again becomes constant. So for all these types of velocity structure, the receiver functions are shown. The response of the receiver functions are shown in the in the in the diagram below. So like for this velocity structure, the response will be this. And for this velocity structure, once
We are not able to hear you.
am I audible now?
Yes, sir.
Okay. So you can see the response of the receiver functions for these three velocity structures are given below. So this receiver function, you can see the converted phases are having pretty much of sharp amplitude, and here the width of the pulse is relatively high if you compare it with this one. That is possibly be happening because the velocity is changing gradually in this case if you compare it with the case of the previous velocity structure, where the velocities are changing pretty sharply in this case. Likewise, if you compare with the response of the receiver functions in the case where you have high velocities and also the discontinuity of type maybe MOHO 410 kilometer discontinuity and also maybe the 660 kilometer discontinuity, then you may see that before the appearance of this pulse, the sharp pulse, because the contrast here is the sharp again, which is quite similar to the velocity structure in the first. But in this case, you have another additional structure having high velocity. So for this structure, the receiver functions amplitude, the additional P2S converted phases will emerge out between the direct P phase and the P2S converted phase. So you can see, so this is the positive amplitude associated with this positive impedance contrast, and this is the negative amplitude associated with this negative velocity contrast. This negative velocity contrast, the receiver function is having another additional pulse that is having the negative amplitude, Likewise, if you will look at the this positive impedance contrast either related to the MOHO or 410 discontinuity or the 660 kilometer discontinuity, then you can see the positive sharp impedance contrast or sharp amplitude again. So if you will compare the amplitude also, you can see that because this positive impedance contrast is pretty much larger than the previous velocity contrast in the same structure, then it is having the highest value. Like among all the converted phases, you are not supposed to compare it with the direct phase because we are talking about the P2S converted phases, the converted phase itself. So this is the largest one, and then this is the second largest one. So this is how you can actually interpret your receiver functions, but this is not always the case because your data is sometimes very noisy, and you will have to perform some pre-processing steps to basically attenuate your frequencies having the noise in the data. So for that purpose, what you will have to do, you will have to perform, you will have to compute receiver functions for many events, many aspect events, and then stack them together. So if you look at, so like for example, if you will just look at let me share it with you.
Sir, your voice is not audible, sir. Again.
One second. So my slides are visible.
Yes, sir.
Okay. Actually, I would have to move my slides. Let's go into the presentation. So if you will just look at the individual receiver function, so like this one that has been computed from an earthquake. So you cannot basically interpret anything out of it in terms of either in terms of P2S converted phases or to actually have a kind of feeling where the impedance contrast might be lying. So, 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 well, in that case, what you will have to do, you'll have to compute receiver function for many of the earthquakes. Let's suppose you took a seismometer and then deployed it into the field for like, let's suppose uh, many years, maybe 2-3 years, and then it has been recording teleseismic event of higher magnitude for maybe quite for some time. So it has, let's suppose it has recorded maybe 100, 200, or maybe 1000 events. And for each of the events, you would like to compute the receiver function, and then you will have to perform stack. So you will have to average out all those receiver functions to get a single value of the receiver function, or you will have to, you want to look at those receiver functions as a function of slowness, or maybe as a function of the package number, so that you can identify some structures that may be lying within the gather of the receiver function. So one of the popular technique for doing so is the H-kappa stacking, which was given by Zhu and Tanamori in 2000. And next few slides that you are going to see are from the presentation of Andy Faceto, and that presentation was given in IRIS on January 15, 2020. So so when I say kappa means you are basically trying to find out the ratio of the p wave velocity to s wave velocity, which means Vp by Vs ratio. So Vp by Vs ratio, in short, it is also known as kappa value. So kappa value is very much important because it is sensitive to the composition, heat flow, and the fluid fraction of the crust. And if you will talk about the common igneous rocks, the VPVS values are 1 are ranging in the like around 1.73 for the felsic quartz granite, 1.78 for intermediate compositions such as diorite, and 1.88 for mafic rocks such as basalt or gabbro. And uh, and and also the BPVS ratio sometimes uh, get raised due to the presence of partial melt of the fluid present in the structure. And using the VPVS ratio, you can also find the Poisson's ratio. It can easily be converted into the Poisson's ratio, and Poisson's ratio is a very common parameter in the earth sciences. So this is the importance of VPVS ratio. And H in the H kappa is taking is the depth of the moho. That means the boundary between the crust and the mantle. So to find the depth of the moho and to find out the BPI-BS ratio, the average BPI-BS ratio of the crust, the H-kappa stacking is performed. So this is the importance of the stacking. So you can see here that so you can see here these are the receiver functions here that are computed from different events. So this is the receiver function for a particular event. This is another receiver function from another event. This is another receiver function from some other event. Likewise, many receiver functions are computed, and this is the stacked value of the receiver function. Yeah. Okay. So you can see there are some current phases. There are some incurrent phases as well. So if you talk about current phases, so there is this current phase you can see very easily here, which is clearly visible. It has distinct amplitude and also current among all the receiver functions. So this actually indicates towards a discontinuity within the subsurface structure, possibly maybe due to the moho, and the phases P2S converted phases. It has been identified as P2S converted phases. Likewise, the PPPS phase also can be identified, maybe somewhere, somewhere there. And the negative phases like PPSS may be lying somewhere here. So here you can see there is a dominant of negative phase impedance, negative phases amplitude. So this may be uh, uh, identified as PPSS. So basically, the stacking is performed to suppress noise and also to emphasize the current signal. And if you perform the stacking, the signal to noise ratio grows by under root of number of receiver functions that are involved in the stacking. So if you are stacking maybe 40 receiver functions, then the signal to noise ratio will be increased by a multiple of under root of 40. So basically, before we actually move on to H-kappa stacking, we need to have some basic knowledge. So if you just talk about the vertically incident S wave after the P wave, so like in this case, then the travel time the P2S convert phase will take can be found out by this integral. So from D depth to the surface 0, it will be find out by 1 by shear wave velocity minus 1 by P wave velocity multiplied with the depth, elemental depth. Okay, so it looks like very easy, right? But it is not always the case. So like suppose you are considering a this H value to be as 40 kilometers, which is generally the case of the depth of the Boho discontinuity. Then, and also if you are considering the average shear wave velocity in the crystal in the crust as 3.5 kilometer per second, P wave velocity as 6.4 kilometer per second, then you can just take the difference of the arrival time of S wave minus P phase. So 40 kilometer divided by 3.5 kilometer per second minus 40 by 6.4 kilometer per second, and which will basically turn out to be 11.4 minus 6.25. That will be around 5.1 second. So from the Mohit discontinuity, the value of the travel time for the P2S converted phase will be around 5.1 seconds. So it looks very simple, but it is not always the case, because you will not always have the vertically traveling wave. So this is not the case. Now the real thing is what actually happens when the plane P wave incident upon a discontinuity, then it is not always vertical. It mostly has the non-vertical incident of the P2S phase. So in that case, there is an extra parameter added to the velocities. That is the ray parameter, which actually is a function of I. If you remember, the ray parameter is the vertical slowness R sin I by B, as explained by Derek in the previous lecture. So this P parameter plays an important role to find out the travel times in case of non-vertical incident. So, so for this purpose, to find out the travel time of the P2S converted phases, so you will have to integrate from D to 0 the travel path from D to 0 under root 1 by Vs square minus P square, that is the ray parameter, minus under root of 1 by Vp square minus P square into dc. So in this case, you will have to know the velocity of P wave, velocity of S wave, and also this value of the P, that is the vertical slowness or the ray parameter of the incident P wave. So in order to, let's suppose if you are talking about the P wave, the timing at which the P wave is traveling, so the vertical component of the slowness of the P wave plays an important role, which is under root of 1 by Vp square minus P square. Vertical component of the S slowness, that is 1 upon Vs square minus P square. If you will multiply this parameter with the thickness of the velocity, the thickness of the layer, then it will possibly give you the travel time of the P wave. And if you will multiply this value with the thickness, then it will give you the travel time of the S wave. So in case of P2S converted phases, this is the travel time of the P2S converted phase. So what you will have to do is because you are talking about P2S and you are taking it, you are calculating the travel time of the P2S converted phase with respect to the direct P phase. So you will have to subtract the travel time of S wave from the P wave, right? So here you have the P wave travel time. Here you have the Here you have the S wave travel time. Here you have the P wave travel time, and then you are subtracting it and multiplying it with the thickness, okay, elemental thickness, and then taking the integral from D to 0, and that will be, if your shear wave velocity is 3.5 kilometer per second and the parameter is 0.06, and the P wave velocity again is 6.4 kilometer per second, and the wave parameter of is around 0.06. Then if you will solve it, then it will come around 5.4 seconds. Okay, so this is how the travel path of P2S converted phase may be calculated. So basically, this formula can be used to find out the time of a phase from a given depth for the phase to actually cover the path from D to 0. So this is for the P2S converted phase. Okay, there are other phases as well for which the formula can be derived. So like now we want to solve for what depth a phase was produced depending on its arrival time. So with constant Vs and Vp that do not depend on depth, arrival time equation becomes like this. Okay, so here you have removed the elemental incremental in the depth and just kept the capital C value. And if you would like to find out the depth, then you will have to have the knowledge of the travel time, and also you will have to have the knowledge of the average shear wave velocity, average shear velocity, and the ray parameter. So from the receiver function, we can easily identify the PS phase because it is almost coherent in all the receiver function completed from many of the events. So let's suppose PDS is 5 seconds, P2S and P, if you will assume around 0.06 kilometer per second for a average Earth model, then and also BP for the average thrust is 6.4 kilometer per second and shear wave velocity around 3.5 kilometer per second. Then you can incorporate it into this formula, and this 5 is known from the gather of the receiver functions. So you will get the value of the depth from which the convergence are happening. So Z is equal to 37 kilometers. So now the question comes, how sensitive is this value of Z to our assumption? So we can vary VP and see how the changes in the H is happening. Okay, so this is the table. You can see the VP is in one column. There is kappa value, VPIVS, there is shear wave velocity, there is a ray parameter, and this is the depth of the impedance contrast for which we are investigating about the for which the value this is the value which we are trying to estimate. So you can see in the first column we are varying the VP value by keeping the kappa value constant and also the ray parameter constant. Ray parameter will remain constant, and we are varying the VP value and keeping the kappa constant. From this, we are calculating the Vs value. So kappa is what? VP by Vs, and VP is there, so we can calculate Vs. So this is the calculated Vs value in this column. So you can see there is some variations in the H value from the variation in the VP value. Likewise, if you will vary the kappa value by keeping the VP constant and calculate the Vs value, then you will see the variation in H, like here. So if you compare both of the tables, so you can see the crystal thickness is varying very. There is a very small effect on the crystal thickness as you vary the VP. Okay, but if you vary the kappa value, there will be a large effect on the crystal thickness estimates. So basically, so you may think about it that okay, if VPIVS is having a large effect on the H value, then we can actually do a stacking that will be depending upon the VPIVS and the H alone to find out the reliable estimates of the H and kappa values. So this is the so basically here. So again you have actually again taken the arrival time of the vertically incident PPPS wave after the P phase. So here we are trying to see the arrival time of the another converted phase that is arriving into our receiver functions, that is the PPPS phase, and because it is having 3P and 1S. So basically 2P and 1S, and that this timing will be seen in relatively to the direct P phase. So we are subtracting 1 by VP and multiplied by GDZ. So from D to surface, that is from the depth of D to the surface, we are trying to estimate the value of the travel time of this PS should be PPPS. I am sorry, this is wrong here. It should be PPPS. Okay, T PPPS. So the formula for the travel path of TPPS will be integral d to 0 1 by VPC plus 1 by VS jet into dz. So you can see this has been cancelled out. Only the remaining thing is 1 by VP, 1 by VS. This is this formula only for the vertical incident. Okay, so likewise, if suppose it is there will be a non-vertical incident, then this formula will be having an additional term, that is the ray parameter term. So the formula will change to this thing for the PPPS phase, d to 0 under root 1 by Vs square minus P square plus under root 1 by Vs square minus P square. So if you compare this formula with the travel time of the P2S converted phases, then what you will see is that you are actually having a plus, a minus sign here, and here you are having just a plus sign. That is because of the pattern of the ray path. Because you have three P path here, here you have only single P path, and then you are subtracting it from the direct P phase. So the formula will come like this for the travel path of PPPS and P2S converted phases. The formula will come something like this. Likewise, you can calculate for the formula for PSPS plus PPSS phase arrival time. So this is so here actually so, yeah. So as I told you, so let's suppose this is the layer, and this is the direct P phase. Okay, we are considering. So this is the direct P phase, and this has actually traveled as P phase into this velocity layer, and then reflected back as S wave, like this, and then again reflected back as S wave. So this is your PPSS phase. So to get the, so here you have 2S and 1 P in the layer. Okay, and that will be subtracted from this incident P, that means minus P, 1 P. So what you will remain? You will get only the 2S, S means under root of 1 by Vs square minus P square into dc. Right. So this is the formula that you are getting here. Okay. So now, if you talk about this receiver function and calculate the respected, calculate the value of the z from different arrival times, then you can estimate it as, so this receiver function that you are seeing is a synthetic receiver function where P2S converted phase is coming at around 5 seconds, PPPS phase is coming around 16 seconds, and PVSS and plus PSPS phase is coming around 21 seconds. Okay, so if you want to calculate the value of the Z from this formula, then it can be estimated as this. So 16 is the arrival time of the PPPS phase divided by under root of 1 by Vs square minus P square plus under root of 1 by 1 by Vp square minus P square, that is the PV velocity 6.4. So when we will calculate the value of the Z from this formula, it will come around 37.7. Likewise, if you will calculate the value of the Z, that is from PSPS plus PPSS phases, so the arrival time of PPSS and the PSPS phases is 21. And if you will incorporate that into this formula that was shown previously as well, this formula, so what you will get is 21 divided by 2 under root 1 by Vs square minus P square, and it will come around 37.6. Okay, so basically, so from all the estimates, all the formulas, So from the arrival time of PS phase, from the arrival time of PPPS phase, from the arrival time of the P2S converted phases, you are getting three different values of Z. Okay, this is the depth of the contrast from which the convergence are happening. So how do we account for these differences? Are they all resulting from an interface at the same depth? Or the phases all picked correctly? So there can be many possibilities why these depths are coming differently. Maybe the phase identification, the type of the phase identification that we are doing in the receiver functions are done manually, and so some human error might be there because of which these are coming differently, or maybe due to some noise it may be happening. So for that purpose, you will have to follow a certain methodology to calculate this depth correctly, together incorporating the constraints from these three different converted phases. So for this purpose, you keep the VP constant and vary the value of VPIPS as we done previously, as we have shown it, because it is the factor that is affecting the most the estimates of the H value. Okay, so for this purpose, you will have to go through a technique that is known as H kappa stacking technique. So these three different contours are representing the amplitudes of the PS converted phase, PPPS converted phase, and the PSPS converted phase. So the different colors. So this green one is for the PS converted phase. Blue one is for the PPSS multiples, and red is for the PPPS phase. And when we are plotting the amplitudes with respect to the varying value of the VPVS, VPIVS, and the crystal thickness, when wherever these contours will actually cross each other, that particular point of intersection will be associated with the true value of the H and the VP by VS ratio. So basically, what is, let me see if my notebook, one notebook. Yeah. So basically, so let's suppose to explain this a little bit more. Let's suppose this is your let's suppose this is the surface of the earth. Okay. Yeah. And you have a station here which you have actually installed for a very large period of time, maybe let's suppose 3 or 4 years. So why you need to install it for that much of time? Because earthquakes happens randomly, and you cannot control the happening of the earthquakes. So to keep it for a longer period of time, so that you can have a sufficient amount of earthquake data into your hard drive. So let's suppose it has recorded this earthquake, it has recorded this earthquake, it has recorded this earthquake. Likewise, it has recorded many other earthquakes. And the earthquakes are sending energy like this, and this has been sending energy like this has been sending energy like this, and this may be sending energy like this. Or so this is your earthquake 1, let's suppose. This is your earthquake 2, and let's suppose this is your earthquake 3, and likewise you have the nth earthquake here. So for each of the earthquake, you can compute your receiver function, right? So this is your receiver function 1. So for this, you have computed your receiver function. For the second earthquake, you have computed your receiver function. For the third earthquake also, RF2, RF3, and this is RFN. Okay. So when you plot these earthquakes together, So if you will plot these receiver functions together, let's suppose your first receiver function is something like this. Okay. And your second receiver function may be something like this. Third one is maybe like this. Likewise, you have much more receiver function, many more. Okay. And you know what is the arrival time of P to S converted phases? The formula T PS that you know. Okay. That is equal to TPS is equal to H in bracket under root 1 by Vs square minus ray parameter square minus under root 1 by Vp square minus P square bracket close. Likewise, you have formula for TPPS that is equal to H under root in bracket under root and 1 by maybe this is Vs square minus P square. Okay, plus so basically under root 1 by Vp square minus P square. Okay. Likewise, you have third formula for TPSPS. Yes, TPSS. So that is like 2H in bracket under root 1 by Vs square minus P. Okay. So from these formulas, what you can do, you can actually take Vp out. Okay. So if you will take Vp out of this formula and in the denominator of H, so you will get Vp out here, and then the numerator term will be multiplied by Vp square here, and this also will be multiplied by Vp square. Likewise, this also will be multiplied by Vp square, and this also will be multiplied by Vp square. So likewise, you can do same thing for this one and for this, same thing for this one as well. So here also you can take Vp out, and here also you can take Vp out. So basically, you will see that your travel time will become a function of this H and this kappa value, Vpy Vs ratio. This travel time also will become a function of H and Vpy Vs ratio. Okay, likewise, this TPPSS also will become a function of H and Vpy Vs ratio. Okay, so only unknown thing will be that this Vp value here. Okay, and this Vp value you can assume for the average crust ranging in between, let's suppose 6.0 km per second to 6.6 kilometers per second, or you can assume this value from the previous studies. Okay, so if you have the knowledge about this Vp, or maybe from the reflection survey, you can find out this value for the average crust for a particular area where you would like to do the investigation, and then you can vary this H and Vpy Vs values. Okay, let's suppose you are varying H from say about 20 to 60 kilometer. Okay, and likewise you are varying Vpy Vs, let's suppose from 1.5 to let's suppose 2 kilometer per second. 2 kilometer, sorry, 1.5 to 2. Vpy Vs do not have any unit, it is dimensionless. 1.5 to 2. So for each combination of H and Vpy Vs, you can calculate this TPS, you can calculate this TPPS, you can calculate this TPSS. So let's suppose you have calculated for first combination your TPS value, TPPS value, TPPS value. Then you will identify those values onto this receiver function. So let's suppose your PS value is somewhere over here in all the receiver functions. Okay. So this is your time. Okay, this is your time. So let's suppose this is the first TPS value for the first combination of H and BPIVS. So, and also you calculated TPPS value somewhere here, and likewise TPPSS value somewhere here for the first combination of H and BPIVS. Then you will apply a formula, that is S H comma kappa, that is equal to W1 amplitude of PS converted phase plus W2 amplitude of PP PS phase minus W3 amplitude of PS PP SS phase, or you may say PS phase. Okay, so the first combination of H and BPIVS or kappa, you can calculate this S value. Here, this negative is because your amplitude of PPSS and PSPS phase is negative. So to have it correctly incorporated into this equation, we'll have to calculate where we'll have to incorporate this negative sign in front of it. And W1, W2, and W3 are the weights for the PS phase, PPPS phase, and the PESS phase. Because PS phase is mostly the clearest arrival onto your receiver function, the weight associated with this one will be higher if you compare it with W2 and W3. And the next significant phase, next significantly clear phase that you will see onto your receiver function will be this one, PPPS. So the W2 will be having little lesser weight than the W1, and W3 is the noisy phase, which is actually sometimes it's clear, sometimes not clear on your receiver function. So this will be having the least weight. So for, as I said, for the first combination of BPIVS, you can calculate this SHK value, and likewise you can calculate for this SHK value for the another combination of H and BPIVS, and then can plot these contours out. So this particular value that you are seeing at the intersection is the highest value of the SHK. Okay, where they are meeting with each other. So ideally it should happen. So this is the real data example you are seeing that I have taken from Zhu and Kanamori, the paper that has been published in 2000. So the data is for a period of 6 to 12 months of the event needed. So it is saying that minimum 6 to 12 months of data is needed to achieve a good solution. So on the y-axis you have BPIVS ratio. On the x-axis you have the value of the H that is varying from 15 to 40 kilometer, and BPIVS is varying from 1.6 to 1.9 or 1.9, and the solution that you are getting is lying somewhere here, and associated value of the H and the BPIVS will be called as the reliable solution for this particular station where the data has been recorded. So you can see the value of H that you are getting over here is around maybe 33 kilometer, and the value of BPIVS that you are getting is maybe around 1.72. So this is the optimal solution, or you can say wherever you are actually receiving the bullseye into your contour plot or between BPIVS and H. So you can also say it is basically a grid search technique where you are making a grid between BPIVS and H. For each grid value, you are calculating the SHK value and then plotting it onto this contour map. And wherever this SHK value is becoming highest, that particular value will be the associated value of H at BPIVS will be the value that you are looking for for the Mohit thickness and the kappa value for the BPIVS ratio. And So like now they have shown like different weights assigned to different phases. So like as I told you, the W1 is the weight for the PS phase, W2 is for the PPPS phase, and W3 is for the last phase, that is this one. So as I told you, the nearest arrival is the PS phase, so the highest weight is given to this one, next highest is given to this one, and the lowest is given to this one. And the solution is this. Likewise, or you may consider, so the one thing that you must remember, the sum of the weights should always be adding up to 1. So 0.7 plus 0.2 plus 0.1 should be equal to 1. Likewise, in this case also, the sum of the weights should be 1. So here also the sum of the weights is also 1. So basically, in the ideal case, it should be like this. The weight should be equal, but because our data is noisy and mostly the PS arrival is observed to be the clearest one, so the highest weight is given to that one, and the next highest is given to the PPPS, and the lowest is given to PPSS or PSPS. So you can see. You can see here the number of receiver. They are showing how the number of receiver function might affect your results. So in this case, you can see the receiver functions that they have taken into account is 173. 173 receiver functions. The H kappa stacking is done here, and you can see the bullseye is achieved here, and also and you are getting a unique solution. But in the case when you are having a receiver functions lower, that means low number of receiver functions if you are using, then there will be uncertainty into your results, and you may not be able to estimate the correct value of the BPY-BS ratio and the Mohit thickness. So this is the summarized HK stacking technique. So first, these are the travel times of different phases, and this is the SKH value that you are actually calculating using these travel times and associated amplitudes. After you sum them up, wherever you are getting the intersection between the different contours of PS, PPPS, and PSPS phases, that associated value of the H and BPY-BS will be the realistic or reliable value of the estimates of the average crustal structure. So these are the uncertainties that you can calculate using these formulas, for which you will have to use the finite difference method and the Taylor's expansion to calculate the uncertainty into your results. This sigma is the variance in the SHK value, and that will be calculated by sigma 2 sigma S divided by del square S by del square H, and sigma K square is equal to 2 sigma S divided by del square S by del square kappa. And from BPY-BS, if you want to calculate the Poisson's ratio, then this is the Poisson's ratio calculation. So this formula can be used, and it is very simple to use. So just you have to use this formula to calculate the Poisson's ratio. So now I am showing you some examples of the work that my student has done in order to calculate in order to do the H kappa stacking. So for his work, he considered the stations that were actually installed on the island of Hispaniola, and this is the tectonic map of the northern Caribbean boundary. So this is the North American plate here, and here you are seeing the Caribbean plate, which is the relative motion between the Caribbean plate and the North American plate is shown by this red arrow. These are the two important earthquakes that happened on the island of Hispaniola, and this is the location of the highest peak in the island of Hispaniola. So my student Sachin Kumar published a paper in Tectonophysics in 2020 about his results, where he used around 7 stations data that were primarily located on the western part of this Hispaniola island. So this island is basically divided into two countries. So on the eastern side, Haiti is there. On the western side, Haiti is there. On the western side, on the eastern side, Dominican Republic is there. So he used 20 stations data, and out of these 20 stations, 17 stations were augmented since year 2014 in DR, and 3 seismic stations were are a part of Canadian National Seismic Network, and he used a magnitude of greater than 5.5, and the events were coming from a epicenter distance of 30 degrees to 95 degrees, and he computed around 686 PS receiver functions that were of good quality. And this is the statistics, the receiver functions for which the earthquake event for which the receiver functions were computed are shown. The distribution of the earthquake on the globe has been shown here. And this is the location, the triangle is showing the location of the network for which the data were recorded. And this is the histogram of the network event. You can see the highest number of events, that is 233, are recorded from a mechanism of in between 180 degrees to around 200 degrees. And next highest number of events, 182, are recorded in between mechanisms of around 160 to 180, likewise. Okay, and then because this is a island, because Hispaniola is an island, so and also it is surrounded by ocean, so most of the data were noisy, all because of the wave action on the Atlantic coast, or maybe due to the literally inhomogeneous structure due to the accreted melange, or maybe due to the presence of a tipping slab. And these were the efforts that he made. I will go directly to the results. So these are the results from HK stacking. So you can see there is this gather for a station, that the location of a station is represented over here by a star, and this is the station location for which the receiver functions are computed. So these are all the receiver functions, and this is the direct P phase here, this one, and here is this is the P2S phase. M is for the MOHO, and this is the again another P2S converted phase, but this converted phase is coming from a discontinuity that is below MOHO. So this is BMD, below MOHO discontinuity, and this is the PPPS phase from MOHO discontinuity, and this is the PSPS or PPSS phase from the same discontinuity. And after he did the H kappa stacking, then he could produce this result. And what he found, that the MOHO possibly beneath this station may be around 26 kilometers, and the PPI-VS ratio may be around 1.8 kilometers. And he also performed some modeling, and he also produced this model and tried to match the observed receiver one function with the synthetic receiver function, and his estimates were quite matching with the MOHO thickness that he estimated from H kappa stacking. And this is the possible wave path diagram for the various converted phases. Likewise, for another station that is having location somewhere here, that is represented by star again. The station code is JIDR, and he again identified some of the phases by looking at the coherency of the phases among all the receiver functions. So this is for the P2S converted phases from intracrustal discontinuity. This is the converted for phase PPPS from the intercrustal discontinuity again. And this is the P2 estimated phase from Mohor discontinuity. When he did the H kappa stacking, then he could find out the reliable H value at around 39 kilometer and kappa value at around 1.89 kilometer. Likewise, he did the modeling and found out that his results were reliable. And then he did the H kappa stacking for another station, PAPH, and found out these results. And this is the gather, and did the modeling again, and to have the conformity of his results, what he has produced. And this is for SGD. The SGD was located somewhere here, and HK stacking results were somewhere here. You can see the Mohor is around 47.8 kilometer and kappa is 1.65 kilometer. And this is the same result for another station, that is SC01 nearby the Pico Duarte peak, as I showed you in the map. And the H that he has produced was around 13 kilometer and kappa is 1.93 kilometer. And this is for SDDR, the same thing. This is for PODR. This is for NADR and MIDR. This is for NEDR, SMDR. This is LGNH and JKH. So I have just kept all these results just to show you. So, after explaining 2, 3, all things are same. So I am just skipping from all these. Just you may just have a glimpse of it. Likewise for SADR and HIDR. This is LEDR, MCDR, and this is MADR. And this is the final map that is produced for the variation of the Mohor depth from the receiver function. So this shows the Mohor depth variations by different colors. And this is the variations in the BPIBS, again with different colors for the average thrust. And this is the table he compiled for the various values of the Mohor thickness and BPIBS for the respective stations. So based on his result, he actually divided his entire area into 4 domains. One is the Southern Dominican Republic domain, which is primarily composed of Batamangli limestone and other marine strata. Second one is the Northern Dominican Republic, which is actually a accretionary wedge. And another one is the Central DR, which is Cordilleras, Central and Oriental, may be composed of igneous and metamorphic island arc related rocks. And the last domain was identified as Southwestern Hispaniola, accreted oceanic thrust or LIP. And this is the cross section that he has produced. So if you look at the map, yeah. So here actually he produced some cross section. So like there was a cross section like this, there was a cross section like this, and there was another cross section he produced like this. So for 2 cross section, we are showing the variations of the Mohor thickness and the PPIBS ratio in this particular figure. So you can see the Mohor is varying beneath these station PODR, NEDR, STDR, SC01. So it is like this. You can see Mohor is varying like this. And these are the PPIBS ratio here for the stations that are shown here. Likewise, for another cross section that they have produced variations in Mohor thickness like this, and the BPIBS ratio associated with that is somewhat like this. So this is just an extra slide, I would say. So this is all for today. Is there any question? Do you have?
Sir,
Yes.
In real results, some stations don't have multiples. So how
Yes.
reliable VP by VS and H values in that case? How you did?
Yes, actually, in the case where the multiples are almost not visible or not present because of the noise in the data, as I told you, our data was very noisy because it is surrounded by the ocean all the way. So in that case, what we did, we kept the weights associated with the multiples pretty low and give the highest weight to the convergence that are clear in the receiver function data. So in that sense, because we kept the low rates for the multiples or the reverberations and much higher for the direct converted phases, then the reliability still because high because we also compared our results with the modeling results that we performed. So it was quite matching. So we can say the results were quite good. But still, to have more accuracy on your results, we did acknowledge the quality of our receiver function by assigning some grades. So you can see in this table the grades are assigned. So like for PCDR, because we could identify all the phases quite clearly, so we gave A grade. For SADR, because we could not identify all the phases altogether, so we gave it a D grade. So we acknowledge that into our paper that okay, the for the stations our receiver function quality was quite compromised, so we are giving a D grade. So the result may need to be improved upon in the future by some other methodology or by incorporating more data for this station. Likewise, for NEDR, we give B grade. Likewise, for SODR, LEDR, we give C grade. So likewise, we have acknowledged that into the paper.
Yes, sir. Sir, which inversion method you used for inverting data? Or
Actually, that was a hit and trial method.
okay.
We did the matching quite manually using the Bauer-1 code. Yes.
Sir, in inversion modeling also, Moho is matching well in some stations, but multiples are not matched in some cases. So is that affect that velocity structure?
Yes, it may affect, but you can, yeah, but like the direct P2S converted phase is matching and associated. So we also actually did not pay much attention to the matching of the multiples. Okay, because we are giving the least weight to this one. So if the direct PS phase is matching, then we can possibly say our results are reliable.
Okay. Thank you, sir.
Yes. Any other question from anyone else?
Sir, one question for you. So
Yes.
when you say receiver functions, you mean the actual seismogram that you receive in the station?
No, no. Actually, the seismograms received on three channels, like vertical component, north-south component, east-west component. So when we do some processing like rotation of the seismogram and deconvolution of the vertical component from the radial component, then what you get is the receiver function. And receiver function contains the impulse response of the earth structure, means the location, the time location at which different impedance contrast may be lying within the subsurface of the earth. So for example, if you look at any receiver function, let me show you the previous figure again. Yeah, this one. So for example, so this is the one which we got after doing the rotation and deconvolution. And these are the P2S converted phases that we are getting. So this is the direct P phase, that means that this one. Yeah. So this is the direct P phase, which is associated with this one. And the convergence, this one, the P2S is for this phase. And other multiples like PPPS, PPSS, PSPS are represented by this one. Okay, so So if you have, so the time difference between the direct phase and the convergence, if you will identify that, and also you will model this amplitude as well, then you can possibly find the depth in the Moho, or maybe another discontinuity from which these contrasts are happening. I hope this answers your question.
Yeah, yes, sir. One more question. So is this method just used to identify Moho, or we can use it for some other purpose as well?
Yes, you can actually find out the shear wave velocity model. You can also find out the BPY BS model. You can also identify. You can also find out the P wave velocity model. So there are several modeling schemes you can actually do, like the previous, like the developer, the girl was saying, the inversion methodology we can use to see the vertical variation of the velocities and the lateral variations of the velocities using the receiver function. There are many methods, like common conversion point stacking technique can be used to identify the topography of the discontinuities within the subsurface of the Earth, like for Moho and LAB. So this is a very good technique to actually see the velocity variations as well as the location of the discontinuity.
Yes, sir. I mean, let's say from 0 to 5 kilometers, can we use this method to identify something?
0 to how much?
Let's say 5 kilometers depth.
For that purpose, you will have to have very high resolution data. Your stations might be located maybe very closely to each other to actually sample the structure in order to have that much of resolution. 0 to 5 kilometers is very small if you compare it with the deeper seismology. So a small scale feature, if you would like to identify like the expression of the fault or beneath the subsurface, maybe up to a 5 kilometer depth or something, then you will have to place your stations very closely.
Okay, sir. Thank you.
Any other question? So I would say this is the end of today's lecture, and in the evening we will do the tutorial. I will send this to the presentation now to you all, and the tutorial, for the tutorial part, I will just explain the MATLAB code, how to run it, how to calculate the receiver function, and also how to do the H stacking. To actually give you basic knowledge about how the results look like in the, like using the real data. So in that tutorial, you will be just watching, and I will be just doing everything and will explain. Okay, so I think because we do not have that much of a for everyone, we do not have that much of computer support as Derek have. Derek have in his lecture. So I hope that would be fine with you all. So now we will meet at 7:30 in the evening. Thank you all.